last 3 sections of our course, we're going to be looking at some things that we've learned in earlier courses, that being polar graphs and polar coordinates, and put them together with conic sections and also with integration. So let's get started with just reviewing polar graphs and polar coordinates. Okay, rectangular coordinates are based on a system of x and y, where that x-axis is horizontal, y-axis is vertical. Polar coordinates are based instead on a radius and an angle. Okay, the radius looks very similar to the x-axis, that kind of measurement, but the angle starts from that positive r-axis and goes around the circle. So when it's pointing straight to the right, that's 0, and as it goes around counterclockwise, it goes from 0 to 2 pi radians. Let's take a look at how we can convert. If we want to go from polar coordinates to rectangular, we just need to remember that x is equal to r cosine of theta. Theta is what we use for our angle. And y is equal to r times the sine of theta. So that's our conversion from polar to rectangular. If I want to go from rectangular to polar coordinates, I need to remember that the tangent of theta, so sine over cosine, is equal to y over x, and that r squared is equal to x squared plus y squared. So those are our conversion factors for both directions. So let's say we have the point written in polar, r theta of 2 pi, and we want to write that in rectangular coordinates. We need to remember that x is equal to r cosine theta. Okay, so we're just going to put in these amounts, and so x is equal to 2 times the cosine of pi. Okay, for y is equal to r sine theta, so we make the same substitutions. Y equals 2 times the sine of pi. Okay? And if you remember on your unit circle, there's 0, and pi is over here, and the cosine of pi is -1. So this comes out to x is -2. The sine of pi is 0. So y is equal to 0. So my rectangular coordinates that go with 2 pi are -2, 0. Okay, let's look at another one. If I have square root of 3 and pi over 6, I'm going to use exactly the same process. So my r cosine theta is going to be square root of 3 times the cosine of pi over 6. So this gives us a value of 3 over 2. My y is going to be square root of 3 sine of pi over 6, which is going to give me square root of 3 over 2. Okay, so that's how we convert from polar to rectangular. Now let's look at converting from rectangular coordinates to polar coordinates. So if I have ordered pair xy that is -1, 1, and I want to rewrite this with polar coordinates, I know that the tangent of y over x, so this would be my theta, is -1. Okay, I just took y over x. Okay, so what angle theta is going to give me a tangent of -1? And remember your unit circle, and the angle 3 pi over 4 has a tangent of -1. Okay, and there are other angles that have that same tangent, but we chose this one because in rectangular coordinates, -1, 1 is in the second quadrant. So we want our answer also to be in the second quadrant, which goes with 3 pi over 4. So we know that theta is 3 pi over 4. To get r is just going to be the square root of x squared plus y squared. So I put the -1 and the 1 in there. I get 1 plus 1. So this is the square root of 2. Okay, so my ordered pair in polar coordinates would be square root of 2, 3 pi over 4. Okay, let's look at another one. Let's look at x, y equals 0, 2. Okay, and this lies on the positive y-axis. So up here somewhere. And so we know that theta, if we're going to be on this axis, theta has got to be pi over 2. And because the y is 2, that means that r also has to be 2. So this coordinate is 2 pi over 2. Okay, now we're going to get a little practice with graphing polar equations. So my first example, I've got r equals 2. And the graph of all the points where r equals 2 is simply a circle with a radius of 2. Okay, how about theta equals pi over 3? Well, on our unit circle, we know that theta equals pi over 3. This is pi over 2. So pi over 3 would look like that. But we also draw it down this way. So this is theta equals pi over 3. And then for a third example, do something a little more complicated. R is equal to the secant of theta. Okay, this is not as obvious as these two were. So we're going to start with this polar equation and change it to our cosine theta equals 1. Well, we know that our cosine theta is x, so we get x equals 1. It's my rectangular equation. And even on a polar graph, x equals 1 is still this vertical line, okay, which is the graph then for r is equal to secant theta. Okay. Sketching these graphs by hand, especially if they're more complicated than this, can be very tedious if you have to pick points and plot them and then connect them. So I'm going to show you how to do that with calculator, and it's very much easier that way. I would suggest that anytime you're working a problem with polar coordinates, that one of your first steps should be to put it in the calculator and see what the curve looks like that you're looking at. Using the calculator to graph polar coordinates is very similar to using it for parametric equations. Just as we did before, we start by clicking on Mode and scroll down to the 4th row. This time, instead of going right to par, we click once more to go to POL for polar. Click Enter, and then second, Quit. Now when I click on Y equals, instead of Y sub 1 and so on, I get R1, R2, and so on. So I'm going to enter the equation from my example, which was R equals 2 cosine 3 theta. So 2 times cosine, and then 3 times, and then I use this button next to alpha to get the theta, and close my parentheses. Now I can click on Graph, and there I have my graph. This doesn't look very well proportioned because the x and the y axes are not the same size. If I want to change that, I go to Window, and I can change at theta min 0 to 6, x min from -4 to 5, and so I can change those numbers to get something that looks a little more like what I want. Okay, going back to the graph, I see that the y units seem to be a little bit larger than the x units. So I'm going to make the x units larger by cutting the graph down to -2 to about 3. So I go back to Window, and then down to the -4. I'm going to change that to -2, and then I'll change x max to 3, and take another look at my graph. Much more proportional now. I could, if I wanted to, extend the graph down a little lower to get the last bit of this petal, but I see enough of the graph here that I'm satisfied with this. We are going to look at a couple of examples of how to sketch a polar graph from the equation. So we'll start with this one. R is equal to 2 cosine of 3 theta, not just theta. Okay, we'll start with the table of values for this one. So when theta is 0, the cosine of 6 times 0 is still a cosine of 0, 1. So R is equal to 2. If theta is pi over 6, R is 0. Pi over 3 gives us negative 2. Pi over 2 back to 0. And 2 pi over 3 gives us a value of positive 2. So we'll start here at angle of 0, radius 2. So right out here. My next point, pi over 6, so that's kind of maybe about like that. But my radius is 0, so we're going this way. And then when we get to pi over 3, we're at negative 2. So pi over 3, about like that. But negative 2 means we're going to be down this way. So about here. Pi over 2, we're back to 0. So we come back up in here. 2 pi over 3. No, this is pi over 2, this is pi over 3, so 2 pi over 3 would be about like that. And we're coming back this way. And if we add a couple more columns in our table, we would get this and this. Okay, and this is called a Rose curve. Okay, Rose curves are, there's a whole group of them that primarily differ in the number of rose petals that they have. Okay, in our next example, we're going to be looking at slope. And we know from our basic calculus that slope is dy dx. And so to write this in polar form, we can write dy d theta over dx d theta. Okay, so this is going to be f of theta cosine theta plus the first derivative f prime of theta sine theta divided by negative f of theta sine theta plus f prime of theta cosine theta. Okay, so this is what we can use to find our slope using polar coordinates. And of course we have to assume that this part here is not equal to 0. So we're just going to have to say dx d theta does not equal 0. Okay, what this gives us is a way to find tangents. So if we end up with dy d theta equal to 0, we're going to have a horizontal tangent. If we do have dx d theta equals 0, that indicates that we have a vertical tangent. Okay, if we end up with both of these true at the same time, that's inconclusive. We don't know exactly what we've got there. So let's find some tangent lines. Okay, I want to find tangent for r sine theta for when theta is in between 0 and pi. We're going to begin by writing the equation in parametric form. X is equal to r cosine theta which is equal to sine theta cosine theta, and y is equal to r sine theta, which is equal to sine theta, which of course is sine squared theta. Now we're going to differentiate with respect to x and y. So dx d theta is going to be cosine squared theta minus sine squared theta, which we can write as cosine of 2 theta, which is 0. Okay, and this is true when theta is equal to pi over 4 or 3 pi over 4. Okay, now let's take a look at dy d theta. Dy d theta is equal to 2 sine theta cosine theta, which is equal to the sine of 2 theta, which is 0 when theta equals 0 or pi over 2. So what does this tell us? We have vertical tangents at square root of 2 over 2 pi over 4 and square root of 2 over 2 3 pi over 4. So there's our two vertical tangents. we have horizontal tangents at 0, 0 and 1 pi over 2. So what does this look like? If this is my coordinate system, here's 0, 0. And we said we had a horizontal tangent there. So let's draw that in orange. And if this is 1, our graph is going to come up like this. And this will be 2. And continue on this way. I'm sorry, this is not 2, this is 1. And we've got a tangent at 1 pi over 2. So that would be up here, horizontal. And then our vertical tangents are at pi over 4, which is here, and 3 pi over 4, which is over here. So we've got a circle with our 4 tangent lines. Let's look at one more example of finding vertical and horizontal tangent lines. This time our equation is r is equal to 2 times 1 minus cosine theta and we're going to say theta is in between 0 and 2 pi. So we're going to let y equal r sine theta and we could also write that as 2 times 1 minus cosine theta times sine theta. Okay, then dy d theta would equal 2 times 1 minus cosine theta times cosine theta plus sine theta times sine theta. So this is now going to be 2 times cosine times 1 is going to be cosine theta minus cosine squared theta plus sine squared theta. And now we're going to change sine squared theta into cosine, so we'll have 2 times cosine theta minus cosine squared theta plus 1 minus cosine squared theta. Okay, and I'm going to factor out a negative. So I have negative 2 times 2 cosine squared theta. So that takes care of that one and that one. Minus cosine theta minus 1. So now we're going to have negative 2 times 2 cosine theta plus 1 times cosine theta minus 1. Now we're going to set this dy d theta equal to 0. So the cosine of theta equals negative 1/2. And the cosine of theta can also equal positive 1. So dy d theta equals 0 when theta equals 2 pi over 3 or theta equals 4 pi over 3 or theta equals 0. Okay, we can go through this same process. For dx d theta, I'm going to say x equals r cosine theta, which is equal to 2 times 1 minus cosine theta times cosine theta, which is equal to 2 cosine theta minus 2 cosine squared theta. And so dx d theta equals negative 2 sine theta plus 4 cosine theta sine theta, which is equal to 2 sine theta times 2 cosine theta minus 1. So that's our final result there for x. And dx d theta. So if dx d theta equals 0, that means that sine theta would have to also equal 0. And cosine theta equals 1/2. So dx d theta equals 0 when theta equals 0 or pi over 3 or 5 pi over 3. Okay, so I'm going to leave that line there and our earlier results. And if we draw this shape, it's what we call a cardioid. Looks a little bit like a heart, but it's not pointed at the bottom. So at this point, 1 pi over 3, we've got a vertical tangent. And at 1 5 pi over 3. We have another one. Those actually are the same line. And then I have up here 3, 2 pi over 3. And there's a horizontal tangent there. And then the last one would be down here at 3, 4 pi over 3. I have another horizontal tangent. I'm going to close this section out with one more theorem. I don't have a problem to work with it, and there won't be a problem like this in your homework or test. But just to show you one other thing about tangents, and this is called tangent lines at the pole. If f of alpha is equal to 0, and f prime of alpha is not equal to 0, then the line theta equals alpha is tangent at the pole to the graph of r equals f of theta. Okay, and this might come up if you have one of those pedaled graphs like that. It goes repeatedly through the pole. It's actually going to have two tangent lines, one that goes this way and one that goes this way. And it's tangent right there at the pole.